Right, I'm going to go through capacitance today as a request was made, and I'm going to try to do it all in one. So capacitance is given through this equation. Capacitance is the charge per potential difference across two parallel plates. How much charge can you store on these two parallel plates? The symbol for capacitance is here, connected with a battery, charged through a resistor. Otherwise, the resistor would just be the internal resistance of the battery anyway. So charged through the resistor, and as electrons move across the circuit, these two plates allow a buildup of electrons. So this is the negative, that's the positive. So that means electrons are going to be moving this way. So you'd get a buildup of electrons here, making that a negative plate, and the lack of electrons on this plate makes it positive. Obviously, they'd be equal charges. And now this allows you to then store the charge there, because if you disconnect the battery, that charge is still there. It's not able to flow because you've broken the circuit, and so you can store it. And normally you'd have a circuit set up like this, where you're charging it through a battery and then you just discharge it through the fixed resistor. Now, you can measure capacitance directly using something called a capacitance meter, just plugging it across, and you can measure the value for capacitance. Like I say, it is the charge per potential difference. The capacitance is also given by this equation, which discusses the structure of the capacitance. So A is the area of the plates. Normally when you see capacitors, they kind of look like these sort of semicircles with the different legs on it. And normally inside that, you've got your parallel plates kind of all twisted up. With something called a dielectric in between the parallel plates. Now, the area of the parallel plates, the larger the area, the greater the capacitance, as we can see from this equation. And the closer the plates are together, the greater the capacitance. Maybe a bit counterintuitive, but if I have my plates very close together, and that's negative and that's positive, then this negative plate here kind of cancels out some of that positive charge, if you like cancelling out electric fields and making them weaker. So this negative plate so close to the positive will make it easier for me to remove electrons off this positive plate, because they'll be partly repelled by this one, even though that's where they're ultimately going. If the plates are really far apart, we don't get the same benefit. And then also, instead of having it kind of empty, we want to fill our capacitor with something. And if we fill it with air, then we just multiply it by E0, which is called the dielectric constant. But we also met it when we did electric fields, because it's also otherwise known as the relative permittivity of free space. How easy it is to create an electric field in a material. It's a comparative measure. So if we want to work out the permittivity of our substance, then we multiply the permittivity of free space by the relative permittivity, which is a number. So it might be your material has a relative permittivity of 7, and if it's got 7, then this whole thing gets multiplied by 7, and so we can have a much greater capacitance, which means we can store more charge for the same potential difference. Now, normally a kind of relative permittivity of 7 would be because you've got a polar molecule. It means it's harder to create the electric field, which means there'll be less repulsion, so more electrons will be able to fit on it. So this is an example of a polar molecule. Essentially, polar molecules are molecules that are polarized. There's one part positive, one part negative, and they can rotate freely. So here we have a polar molecule happily minding its own business. And then if I plug potential difference across it and say make this plate negative and this plate positive, these polar molecules will align, and as they align, the positive part of it swings round because it's attracted to the negative part of the plate. The negative part therefore ends up pointing at the positive part. So the electric field created by this is opposite direction and therefore has a cancelling out factor for the electric field from my capacitors. And if it's cancelling out that electric field, it means I can jam more electrons on here and store a much greater charge for a given potential difference, which makes my capacitor better. So to look at the energy stored in a capacitor, we look at the charge potential difference voltage graph. As you increase the potential difference across a capacitor, more charge is stored. And because energy is charge times potential difference, the area under this graph is equal to the energy stored on the capacitor. The area on this graph, if we've got here the final potential difference or the potential difference at any given point and the charge on the capacitor, the energy is going to be half QV, because that's the area under the graph. Energy it's essentially because the half bit represents the average point there, so the average charge and the average potential difference, which is something that I think we did back in we did average and instantaneous velocities back in mechanics. Anyway, so energy is half QV, We can sub that equation back in there and say we swap out the Q for CV and we get half CV squared, or we can swap out the V for Q over C and we get half Q squared over C. So there's lots of kind of practical applications of capacitors. Now, the graphs for capacitor charge and discharge. So there's this equation here that's the equation for capacitor charge, right? For Q is Q0 1 minus E to the power of T over RC. Now, for something charging though, that equation, if you were to plug it in, would look like this, right? It's exponential increase. The same for the potential difference across the capacitor. It exponentially increases until eventually it will match the potential difference of the battery. The charging current though decreases. So initially with all these capacitors, when you plug them in, loads of current will flow, but eventually current will stop flowing once the capacitor has got the amount of charge it can store for that potential difference and no more. So we get a kind of graph that looks like this, exponential decay. Discharging is the same. All three graphs look the same for discharging because the current decays exponentially with time, the potential difference across the capacitor decays exponentially, and the charge on the capacitor decays exponentially, right? And this is the equation for capacitor discharge. Now, in the exam, they give it as Q is Q0, but Q0 represents kind of this point here, the kind of max charge, right? But often you can write it's the same equation if you do V0. So the voltage at any particular moment is V0 e to the minus T over RC, and V0 would be this point here, or that point there, or I0, right? The charging and the discharging both follow this one for the capacitor discharge because it's exponential decay. Now this thing here, RC, now that R is the resistance of the resistor that our capacitor is charged or discharged through, and C is the value of the capacitor. And this thing, the resistance times the capacitance, is an interesting quantity. So for a starter, it's interesting because its unit ends up being the same as the unit of time. If you look at the units of this, so if I kind of do it quickly here. So if we say resistance times capacitance, well, resistance is just voltage divided by current because V is IR. Current is charge per unit time. So I can, instead of saying V over I can say VT over Q, because current is charge over time, and then if we're dividing by that, it's the same as multiplying by time times charge. And capacitance from up there is Q over V. So you can see if we merge these units together, we get RC has the units of VTQ over QV. So the QV's cancel and we just get RC is the units of time. So it's the time constant, so it's the physical time. You might have a time constant of like, say 5 seconds. Yes. Now, when we do some kind of math with this, we can plug in some specific values. So for example, what about like if our time constant is say 5 seconds, what happens when our time is also equal to 5 seconds? So when T equals RC, so we've got time is equal to the value for RC, right? Which could be 5 seconds, could be 30 seconds, could be like a millisecond, right? But when our time equals RC, we can kind of interrogate this equation a little bit more. I'm going to use V for it because charge is not quite so easy to measure. So V is V0 e to the minus. Because T is RC, I'm going to sub it in, RC over RC. Well, RC over RC is minus 1. So V is V0 e to the minus 1. Now, e to the minus 1, that's just a number. Plug it in your calculator. And e to the minus 1 is 0.37. So V is V0 times 0.37. Now, that's telling us that the potential difference at any given, at this time, when time is equal to RC, the potential difference has fallen to 0.37 of its original value. So for the discharge, when V is equal to 0.37 times V0, that means the time that's passed must be equal to the resistance times the capacitance. So from a graph of capacitor discharge, you can work out the value of the capacitance, if you know the resistance, just by looking at that. You don't get given this number, 0.37. You can just memorize that and to say that when the time equals RC, it's 0.37. It's fallen to 0.37% of its original value, essentially. you can kind of have a look that from this equation, you get the sort of like opposite, the remainder. So when it actually falls to 0.63 of the maximum value, that's in this case when RC is passed, right, for the charging, because it's 0.37, but here we've got 1 minus that value, so it's going to be 0.63. Now, the other thing we can do with it is to figure out the half-life. So, well, it's not the half-life. The time to halve is similar to half-life. So the time it takes for the voltage to be half of its original value. So we start off with V is V naught e to the minus t over RC. Now, when the voltage is half its original value, this value, V over V naught, is going to be equal to a half, right? Because you've got the current potential difference divided by the original potential difference, and if it's fallen to a half of its original value, V over V naught is going to be a half. So a half then equals e to the minus t over RC. Now, this is when I've got to use my ln to kind of unpick this equation and rearrange it and find out what that value of t is. And so I get ln of a half is equal to ln of e to the minus t over RC. Well, that essentially, ln undoes the e function, and we get ln of a half is equal to minus t over RC. Now, ln of a half, that's just a number, right? It's actually minus 0.69. So minus 0.69 is equal to minus t over RC. So we can get rid of the negative values, just to make life easier. And then we multiply the RC on this side, and so we get the time to halve. Sorry, as soon as I did this, I should have said that this t is actually the time to halve, because it's not just a that's not just a variable t. That's not any particular time. This is a specific time. It's the time that the voltage potential difference has fallen to half its original value. So the time to half is going to be 0.69 times the resistance times the capacitance. So as in on these graphs, and it's the same for Q naught, it's the same for I naught. So the time for the current to fall to half its original value, so I naught over 2, what you get there is 0.69 times RC. That time there is going to be the time to half. The same for all these things. Now, again, this thing, they don't give you that equation, but it is in the spec, so they do expect you to be able to use that. So you've got to remember, the time to half is 0.69 times the resistance of the resistor that you're charging or discharging through, times the value of your capacitance. That is it. If there are any questions about it, just like write a comment and I can make another video going in more detail. If you want me to go over it again, you can watch the video again, I guess. But I'm happy to have a go at explaining it again if it wasn't clear enough for you.